The more we observe and study our planet, the better we understand it and care for it. Satellites used for Earth observation can measure ground temperature, rainfall, cloud movement, and snow cover. They can monitor the state and evolution of our environment, land and sea. Data gathered can help us to understand weather patterns, monitor air quality, track and predict the effects of climate change. The satellites track the impact of extreme weather and natural disasters like fires, drought, and hurricanes. We can understand better areas at risk, make predictions about future events, and coordinate a rapid response. The satellites carry remote sensing technologies to take their images, and as satellite imaging improves, so do our observation. This is where our project comes in. I'm here at one institute of the Italian National Research Council in Florence. Together with other partners from France, Italy, Germany and Switzerland, they are working on a component that could have a huge impact on science. Surprise is working on a new type of sensor for a satellite. Leading the team is Valentina Raimondi, together with project manager Donatella Guzzi.
This project is really at the forefront of innovation in the Earth observation field. We are working on the construction of a demonstrator which can display a combination of technologies used in this context for the first time. This is the demonstrator. There are two stages. The first is how the picture is taken, which is using this piece that is the core of the demonstrator, spatial light modulator. This is in fact where the image is coded by using a combination of pixel patterns. Each coded image is subsequently integrated and measured as a whole. The next step is how the image is reconstructed from the series of integrated measurements. A compressive sensing algorithm is used to reconstruct the image.
The optical setup of a demonstrator acquires image at different wavelengths, both in the visible and infrared spectral range. The demonstrator uses different detectors and acquires the whole scene thanks to the movement of a target. We do this thanks to the use of a target scanning system. The master unit then puts it all together. It will synchronize the various elements, the acquisition of images, the spatial modulator functions, and the movement of a target.
The work isn't just being done here. Researchers and technicians across Europe are collaborating to deliver the demonstrator. In Germany, our colleagues from Fraunhofer IPMS are working on the spatial light modulator.
A spatial light modulator, or SLM, consists of an array of thousands of individual movable micromirrors, each of them with a size of only a few micrometers. Every single mirror acts independently as an optical valve and can modulate light intensity to create digital images that can be reconfigured in a dynamic way. The SLM technology is the best technology to support a special image acquisition at the SURPRISE project, because we can generate variable image patterns at a high speed. These patterns are overlaid to the image of the observed scene, which can be recorded by a single pixel detector. And beside the demonstrator, we are working in parallel on the development of a new SLM concept which is suitable for space and covers a broad spectral range from the visible to the mid-infrared.
And meanwhile, in Switzerland, XEM is concentrating on the hardware.
We've been working part of the SLM, the commercial off-the-shelf digital micromirror device, COTS DMD in short. A DMD is an extremely precise light switch that enables light to be modulated digitally via millions of microscopic mirrors arranged in a rectangular array. We are adjusting it to surprise to ensure low absorption and high reflectivity in infrared, which is essential for realizing the demonstrator. How are we doing this? We will substitute the original glass window inherently incompatible with our aim. In Surprise, our window will be made of sapphire. This will ensure better transmittance in the spectral range that we need.
Valentina told us that the demonstrator has 2 stages of work. Now over to Turin Polytechnic so that Enrico can tell us how compressive sensing and image reconstruction work.
Here in Turin, we're working on image reconstruction. Our algorithms will receive data from satellites and transform them into images that can be used for Earth observation purposes. These algorithms do something quite new. Rather than acquiring pixels, the demonstrator acquires combinations of them, which have to be unscrambled at the ground segments. We adopt artificial intelligence methods to learn the best possible unscrambling function from a training dataset. In this way, we maximize accuracy and spatial resolution of the reconstructed image and achieve secure data encryption. We also develop methods to extract information from the acquired data directly on board the satellite.
About half an hour from Florence, there is another team of experts working on another element of the sensor, the target scanning system. Let's go and meet the team from SciTech.
Target scanning system was designed and developed to carry out test and validation activities for the Surprise demonstrator. It has a high precision motorized mechanical structure supporting different types of targets used to test the demonstrator in the visible, near visible and infrared spectrum. It's driven by a control unit, which includes all the electronic components and the software used to send command, move the target and set all the configurations. It can be also controlled from remote by HTTP web requests. The main challenges we faced during the development was to achieve a really high precision. In fact, we need very small errors with a repeatability and an accuracy in terms of micrometers. Also taking into account the different type of weights and loads that the different target has to handle. A technical challenge indeed, but also a great opportunity for innovation in Surprise.
Quicker and more accurate data from satellites can help with the early detection of dangerous phenomena, and as such, for a quicker deployment of suitable countermeasures. In simple words, with high speed and accurate data, we can perform better Earth observation. Surprise is really an innovation, a disruptive innovation in this field, bringing together advances in compressive sensing and spatial light modulator technologies, as well as in encryption capabilities and onboard capabilities. Our goal is to enhance the European operational services in terms of encryption capabilities, onboard capabilities, as well as spatial resolution.
The science behind this project is quite remarkable, as is the commitment by scientists and researchers across Europe. We are all looking forward to seeing its evolution into an instrument that can revolutionize Earth observation in years to come.